6.1c and d, we're going to calculate the standard deviation of a discrete random variable and interpret what standard deviation is for that variable. Let's talk about the variance of a random variable. Remember from chapter 1, variance was sigma squared or s squared. This is the variance of the population, is the sigma value. And what it is on average the squared deviations, which would be your piece of data minus the mean squared, of the values of the variable x from its mean, which we call mu, which is the mean of the population. And also recall that sample variance has a very similar definition, but in terms of the notation, we use s squared. So s squared is the sample variance, sigma squared is the population variance. So if you were asked to find the variance of a discrete random variable, what you would do is this formula. Take the piece of data minus the mean and square it and times it by the probability. You're going to do that for the next piece of data minus the mean and square it times its probability, and you're going to do that for the entire data set. Now this formula right here you will find on the AP formula sheet. Let's talk standard deviation now. Remember standard deviation. Variance was sigma squared. Well, standard deviation is just sigma. So what it is the square root of variance. And what it does is it measures how much the values of the variable tend to vary on average from the mean. Again, for the population, a standard deviation is sigma sub x, and then it's for the sample, recall, it is s sub x. To find standard deviation, therefore, once you have the variance answer, all you have to do is come in and actually take the square root of that, and you have it. Let's revisit the NHL information again about the number of goals per this game and the probability of getting that in this distribution. So here they want us to compute and interpret the standard deviation of the random variable x. So before we do that, the first thing we have to do is compute the variance. So remember, variance is sigma squared. And what we're going to do is we earlier did compute the mean for this distribution. And the mean for it, our mu sub x, was 2.851. So for standard deviation, we're going to take each outcome minus the mean and square it, and then times it by its corresponding probability. So what we're going to see is this calculation right here. 0 minus the mean squared times the probability. We're going to add to it every element. Again, the AP board wants you to show some of the work. You can do dot, 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 and wrap up with the last one. When you do that, the variance, therefore, is going to be 2.66. Now, to find the standard deviation, we can easily wrap that up and just take the square root of that variance and get 1.63. So let's go ahead and wrap it up and define it in context. So 1.63, what it means is that, on average, a randomly selected team's number of goals in a randomly selected game will differ from the mean by about 1.633 goals. Now I want to show you how you could actually compute the standard deviation using your calculator if you don't want to do it by hand. We are going to end up using the one variable statistic to do that, like we did back in chapter 1. What you're going to do is do stat edit, and you're going to enter list 1 and list 2. You're going to make the goals list 1 and the probability list 2. Again, make sure you keep these paired up so they look like ordered pairs. Then you're going to wrap up and you're just going to do stat, calculate the one variable stat. Now it defaults by looking at list 1, so we need to tell it to look at 2 lists. If you're in the old operating system, you're going to have one variable stat do list 1 comma list 2. Otherwise, when the screen pops up, make sure you select list 1 and list 2. When you hit enter, you're going to get the standard deviation. Remember, we are looking at sigma sub x, which is right here. And you're going to notice they don't even give you a sample standard deviation. The calculator recognizes that this is a probability distribution. And there is your standard deviation. Now, let's review also, what if you wanted to plot this so it looked like a histogram, or you wanted to see the probability distribution? Well, recall, we've done histograms before, where we go into second stat plot, and we actually choose the histogram selection. But in this case, because we have list 1 and list 2, all we do is the same thing. Do second stat plot, go into the actual screen to make the graph, turn it on. Now instead of choosing list 1 and your frequency is 1, do list 1 and list 2. And then just do your zoom statistics. Now I did adjust my window, so I went into the window button and I changed it to go from -1 to 10, and I wanted it to count by ones, so it'll actually put them in the correct bins. And then if you want, you can adjust the Y scale. The highest probability I said was 0.3, which we're going to see somewhere within this range. It's not going to exceed 0.3. And you actually get a nice looking probability distribution. You don't necessarily need to know how to do this on the calculator. It's just kind of a nice review. This particular slide about using your calculator to create a random variable, I'm not going to really talk about. If you're interested on how to create a normal distribution per random variable on the calculator, these are the calculator steps. Here's an approximately normal distribution. Here's how you can have your calculator create it. Personally, I wouldn't worry about this slide and just skip it. Now let's talk about continuous random variables. Remember we did discrete earlier, which was basically counting numbers where there's blanks in between our various outcomes. Continuous is different. Continuous takes all the values in the interval of numbers. The probability distribution of x is described as being a density curve. So we saw density curves earlier in chapter 2 when we did normal CDF probabilities. When you do normal CDF, it's because it's a continuous random variable which created a density curve. In this case, the probability of any event is the area under the curve and above the x axis that make up the entire event. That is, it assigns probabilities to intervals of outcomes rather than to individual outcomes, as we saw when we were talking about discrete variables. So let's look at these 6 examples and just identify which of these 6 is discrete and which is continuous. So if you are counting numbers, you're going to count 1, 2, 3, 4, 5. Would this be considered continuous or discrete? In this case, this would be considered a discrete value. If you're measuring something with a ruler, we could have 1.2 inches, 1.25 inches, 1.2567 inches. You could have an incomplete interval of measurements. So in this case, we are actually talking continuous. Number 3, the number of hurdles cleared on a 110-meter hurdles. This is about the count of hurdles. You can't clear 1.5 hurdles. You can only clear numerical counting calculations. So this is discrete. The time that it took you to run the 110 meters for those hurdles. Well, the time could be any value. It could go down to the 100th, the 10,000th. It could go to any decimal point on that. So this is clearly continuous. Now, a student's age versus the number of birthdays you have. Let's actually do the number of birthdays first. Your number of birthdays, you're either going to have 16 birthdays, 17 birthdays, 18 birthdays. This in its case is going to be considered discrete. Now when it comes to age, you might think this is discrete, but think of a little kid who's 6 years old in a couple of months. Means they're going to be 7. If you ask a little kid and they're not exactly 6 years old, they're going to tell you they're 6 years old and 2 months, 1 day, and 4 hours. They're going to be very specific and give you a range in between 6 and 7. So for this one, we would actually say the student's age could be considered continuous. Let's do this example here. We're going to let x be a random digit from 0 to 9. So if it's a random digit from 0 to 9, is that discrete or continuous? Good review question. It's considered discrete. And this is what we have here is a graph of between 0 and 9. We're going to notice that there are 10 intervals. Each interval has a probability of 0.1. So this is a complete probability distribution. It's called uniform because it's just what it looks like. It's uniform across from the start to the end. So let's say they wanted us to find the probability that this random variable is in between 1 and 3. And I'm going to put that it's equal to and includes it. So if we do that, we can look at this uniform distribution. If it's 1, it's this. 2, and 3. You could add those up, and the answer is going to be 0.3. Okay, I want us to look at a second scenario. I'm going to give you a different distribution for this, because this is the distribution for random variable x. Let's define random variable y as being any random variable between 0 and 1. So I'm actually going to sketch a different distribution for this. And here's what the probability distribution could look like. Now, would you say, is this one continuous or discrete? So on here, we can have any value between 0 and 1. In this case, we are actually considered that this would be a continuous situation. Now, let's go ahead and look at these two questions here. Find the probability that y equals exactly 0.7. Well, 0.7 is probably going to be about right here. Now, if y equals exactly 0.7, that would be a point on there, not an interval. Here's the key thing to remember. On continuous distributions like normal CDF, we never did normal PDF, which is a point. You can never find one distinct point on a continuous curve. So in this one, you can't do it. That would only be something you could do for discrete. Fine, we can't do that. Let's look at this. Let's find the probability between 0.3 and 0.7. So that we could do. 0.3 is here, so they want to know the area under the curve between 0.3 and 0.7. Well, if this is a uniform distribution, then we know this entire area is 1. We want the area between 0.3 and 0.7, and that is 4/10 of the entire curve, so the answer here would be 0.4. Now, I will tell you, you rarely do see uniform distributions on the AP exam, but every now and then you will see some type of multiple choice question related to it. Let's look at the weight of a 3-year-old. The weights of 3-year-old females closely follow a normal distribution, with a mean of 30.7 pounds, standard deviation of 3.6 pounds. We randomly choose one 3-year-old female and call her weight X. So that's our variable, is the weight of the one 3-year-old. Find the probability that a randomly selected 3-year-old weighs at least 30 pounds. Now, we did this work back in Chapter 2, so this is just a really good review. Let's do state, plan, do, and conclude. What do we want to state? Well, we want to find what's the probability that a randomly selected 3-year-old female weighs at least 30 pounds. Fine. What's our plan for that? Well, let's define the variable. We're going to define the variable as X, which is the weight of the 3-year-old female we chose. And we have a normal distribution. Remember, that's our shorthand with our mean and standard deviation. Well, what do we want to do? We want to find the probability that X is greater than or equal to 30. So we'll standardize this weight and use Table A to find the shaded area. So let's talk about how would you do that in the do portion. I first want to highlight this graph. Remember what we did. We did in a normal distribution. Here's the mean. They define the standard deviations. There's 1 deviation, 2, and 3. We want to find if the weight is 30 pounds or heavier, so we want this shaded region. Now, if you were to standardize this value, this is good review, but not necessarily what you need to do. The z-score for this is going to be negative 0.19. So let's just review where that came from. Remember, z-score is going to be your piece of data. Here it's going to be minus the mean, which is mu, over the standard deviation of sigma. So we took the girl's weight, which was 30 pounds, minus the 30.7 mean over 3.6. When you do that, that's a standardized score. So we know she's below the mean by 0.19 standard deviation. So if this is the mean, she's just slightly below it. Well, we could use Table A if we wanted to. From Table A, we're going to find the actual z-score, and it says that the z-score probability is going to be about 42.47%. So that's what this red region is. Therefore, we can take 1 minus that probability, and we're going to get the actual answer of 57.53%. Now, I think this is a great method to do if they're showing you an example and you have to follow it, but I'll be honest with you, I'm going to use the calculator. So let's review the calculator directions for that. On the calculator, we're going to use second distributions. In second distributions, choose normal CDF. Remember, you put lower bound, upper bound, mean, and standard deviation. Now, you could choose to use the standardized z-score, or you can just actually use the raw data. So I'm going to show you if I just kept the statistics there. What I'm going to do is I want from 30 pounds all the way up. Here's the mean and standard deviation. From there, I'm going to get the same answer as I got before. Now, recall, I can also use Normalcdf, and I can use the z-scores in here. So if I do that, what that would look like is I would just write the Normalcdf. In terms of z-scores, I'm at negative 0.19, and I'm going to go all the way up to the highest z-score possible. Now the mean and standard deviation of a z-score, it's standardized data, so it's 0 and 1. If I put that in my calculator, I will get the exact same answer. So either method is fully acceptable. Okay, let's wrap this up with the conclusion. So what I can conclude is this. There is about a 57% chance that a randomly selected 3-year-old female will weigh at least 30 pounds. All right, let's review another one. Find the probability that a randomly selected 3-year-old weighs between 25 and 35 pounds. So I'm back to the same curve. 25 and 35 pounds is this region. Now to find this region, what I know is the shorthand probability formula is the probability of my variable x's being 25 and 35. Let's just again review what if we use the table for this. If we use the table, I would want to convert and standardize these statistics to their z-scores so I could actually compute their appropriate z-scores. So what we have is negative 1.58 here and positive 1.19 here. How would I find that probability? Well, what I would do is I would actually use the table, find the z-score for this and the probability, find the z-score and this is the probability, and I'd subtract the little tail from the big answer here. So what you're going to see I show for the table is this. I found the z-score of 1.19 was 88.3%. That's this entire region. But then I also found that the probability of the negative z-score, which is this tail, was equal to 0.051. So then what do I do with that? I take this minus that, and I'm going to get the appropriate response for that. And the probability is 82.59%. Again, if this problem was really on the AP exam, what would I do? I'm going to use my calculator. But if you use your calculator, be incredibly careful about calculator speak. Instead of showing all of this work, if you just typed and wrote this down on your paper, you would be fine. This is what I type into the calculator, my lower and upper bound, my mean and standard deviation. However, you must make sure to highlight what I wrote in the purple. You have to identify this is the mean, this is a standard deviation, and you must say it's normally distributed. You therefore have to talk about the shape, the center, and the spread, which we learned about in chapter 1. Review one more. What if they want us to find the probability that x is less than k equals 0.8? Well, what that means is the area under the curve. This is the reverse. So at what weight am I talking about that 80% of the kids are going to be under? Well, it's some weight right into here. Well, how do you find that? Well, you can use your table A, and let's just review that. So for table A, we're trying to find what's the z-score that goes with this spot such that the area is 0.8. If you reverse the use of table A, you're going to find the z-score is 0.84. Okay, fine. But I want to know the weight of that student. Fine. Let's use the z-score calculation and back into the raw data. So I can find the raw score for x. What I'm going to do is put the z-score here, piece of data minus mean and standard deviation. When you solve for this, you're going to find that the actual score, or the weight, is 33.724 pounds. Okay. So we could make a conclusion, and we could say 80% of 3-year-old females' weights are about 33.72 pounds or less would be a good conclusion. Now again, what if I don't want to use table A? You can also use the calculator quite nicely. Remember, the calculator keystrokes are this. What you would want to type or write down is you're going to do second distributions. You're going to find inverse norm. And on inverse norm, what you type is the area under the curve, the mean, and the standard deviation. If you use this calculator speak, again, you must label this as the mean, that's the standard deviation, and you must say that it's a normal distribution somewhere. This will therefore kick out the exact same answer that we got before, and that is appropriate work to actually show.